Welcome back. So this is lecture 55 in this course on Bayesian modeling. The topic of this lecture is estimating Bayes factor using bridge sampling. This is an important lecture because this is what we use in practice for calculating Bayes factors and effectively for doing hypothesis testing in the Bayesian framework. Okay. So especially for the kind of hypothesis we test in behavioral sciences, we often use Bayes factor analysis, and this is the actual practical package that you can use because we often deal with complex models. Okay, so just to recap why we are talking about Bayes factors and its estimation, just to recap, suppose you have some hypothesis that, let's say, some variable x or some factor x significantly affects y. Okay, so let's say there is a significant effect of x on y. Okay, so x is a predictor, y is your dependent variable, and let's say you have a Bayesian model like this, that y I, let's say ith value of the variable y comes from, let's say, some distribution f of theta. It could be, for example, normal mu sigma theta I, such that theta I is a linear function of x. So let's say theta equals to some function, let's call it g. It could be a simple linear function, or it could be, let's say, exponential function, right? That will depend on what kind of parameter theta is. So let's say alpha plus beta into xi. Okay, so let's say this is your model. Okay, this is basically a regression model. Okay? Now this model captures the idea that x significantly affects y. What would that mean? If beta is, let's say, positive, then with values of x, y increases. So as x increases, y increases. If beta is negative, then as x increases, y decreases. So that's the kind of relationship we get, right? Now when we fit this model to the data, we get some posterior distribution for this parameter beta. So let's say for parameter beta, the posterior distribution looks something like this. It's in positive range mostly, but there is some probability mass which is in the negative region. Okay. Now you cannot conclude much just looking at this posterior distribution. All you can say is that the data is consistent with the hypothesis that x positively affects y, as well as with the hypothesis that x negatively affects y, right? So you cannot conclude much from this. You cannot talk about evidence because this does not quantify any evidence for this hypothesis. Because in order to talk about evidence or to claim that this hypothesis is correct or not given the data, whether there is support for this hypothesis or not, you need to compare it with some null hypothesis or some reference or baseline model. In Bayesian framework, it could be any competing candidate model. Okay, so you cannot conclude much from 95% credible interval. So how would you test this hypothesis then? What you do, you can build a null hypothesis model. Okay, this null hypothesis model will be nested within this model. Let us call it M1. Let us call it effect model. So your null hypothesis model will be nested within this effect model. How? What do I mean by nested? So this model would look same in terms of its likelihood. Yi would still come from f of theta I. So that is all fine. Theta I would be g of alpha plus beta into xi, such that beta equals to 0. So that's the difference. Here beta would have some prior, alpha would also have some prior. Here beta is fixed at 0 and alpha would have some prior. Okay, so that's the difference. We set up this parameter beta to be equal to 0. What does this mean? That there is no effect of x on y. Basically, the effect of x on y is 0. Okay, that's the assumption in this model. So if your effect model M1 performs better than model M2 given the data, then you can safely conclude that there is some evidence for the assumption that x significantly affects y compared to an assumption that x does not affect y. So actually what we are quantifying is that how much evidence is there against the hypothesis that the effect of x on y is 0. Okay. So that's how we do hypothesis testing in the Bayesian framework. But the question is, how do we compare model 1 and model 2? So for these kind of models, especially for nested models, Bayes factors is a very good solution. So technically, Bayes factor computes predictive accuracy of the model based on its prior predictions, not based on posterior predictions. So it's sensitive to the choice of priors, for example, here on parameter beta, because that's what differs between the nested model and the null model. So what you can do, you can compute Bayes factor for model 1 over model 2. So Bayes factor for model 1 over model 2, which would be ratio of marginal likelihood of model 1 and model 2, right. So once you compute marginal likelihood of each model, you can take the ratio, that would be your VF12, right. So if Bayes factor in favor of model 1 compared to model 2 is greater than 1, then M1 is better. If BF12 is less than 1, then M2 is better. Okay. Of course, we take some criteria, some conventions that if Bayes factor is between 1 and 3, we cannot conclude much. This is anecdotal evidence. If it is between 3 and 10, let's say it's a moderate evidence. If it is greater than 10, then it's a strong evidence, right. So we take some conventions into account, right. So this is what Bayes factor is. But as I said, Bayes factor is highly sensitive to the prior, because what we are measuring here, it's based on prior predictions of the model. So if prior changes, prior predictions will change and the model's performance will change, right. So that's why when we compute Bayes factors, we compute multiple Bayes factors corresponding to each prior on beta. So let's say prior on beta here is, let's say, normal 0, 1, here it is normal 0, 5, here it is normal 0, 10, here it is normal 0, 20, and so on, right. And you might get your Bayes factor plot like this, right. So you can, for example, claim that, let's say, under these prior assumptions there is evidence for model 1, under these prior assumptions there is no evidence for model 1. Okay, so that is totally fine to claim in the Bayesian framework, and this is actually more informative as well. So under the assumption that, for example, effect size is reasonably small, you get some evidence for the model. When you assume the effect size is large or very small, then you don't get evidence for the model. Okay? So that's understandable. Now, why I'm saying that Bayes factors are useful for comparing models which are nested. These are nested models, because what is happening in these models, they are exactly same. They just differ only in terms of one parameter beta. Okay, so they differ only in values of this parameter beta. So in model 1, beta is some prior, in model 2, beta is 0. That's the only difference between these two models. So these are called nested models. So for example, models which have exactly same structure but they differ only in couple of parameters, those are called nested models. Why Bayes factor is useful here? Because here you know exactly which parameters differ between these models. So in this case, beta is the parameter which differs between model 1 and model 2. So in this situation, you can tightly control the prior. Basically, you can calculate Bayes factors under different prior assumptions on beta. But imagine that you had two models which are completely different. So let's say model 1 is something like f of theta I is g of alpha plus beta xi, and model 2 is yi comes from, let's say, q of phi I, such that phi I equals to h of, let's say, alpha dash plus beta dash xi, right. Now the parameters are different, the likelihood is different, the interpretation of these parameters are different. So these two models are completely different in structure as well as the kind of parameters they have. So when you would want to compare this model 1 with model 2 using Bayes factors, you will need to take into account prior assumptions on all these 4 parameters. So let's say if you're trying 5 different prior assumptions on each parameter, then you will have to take into account 5 into 5 into 5 into 5 number of prior assumptions. Okay, only then you would be able to compare them. Okay, so it becomes very difficult and almost impossible to do model comparison when you have non-nested models. But having said that, you can do it. It's not nothing that technically does not allow you, but just that it becomes computationally very difficult, right? But when models are nested, then Bayes factor is very handy. Okay, and this is the kind of models we have in analyzing experimental data, or the kind of hypothesis we are interested in. So we often do this null hypothesis significance testing. So the equivalent of null hypothesis significance testing in the Bayesian framework is this, that you set up your effect model, then you set up a null hypothesis model by setting up beta equals to 0, and then you compare them using Bayes factors. Okay. Now the goal of this lecture is to show you that how to do Bayes factor analysis in practice. So basically, for actual example, you'll have to fit a BRMS model and then use the output of the BRMS model to calculate Bayes factors using a bridge sampling package. Okay, so bridge sampling package is useful when you have complex models. For simple examples, I showed you some Monte Carlo integration methods so that they can work for simple examples. But as you go towards more complex hierarchical models, you would require some more sophisticated packages. All right, so we can take the same example as we did in the previous lecture. So I'm loading these two libraries, bridge sampling and BRMS. This is the data we had. We were trying to model number of road accidents in a city over last 5 days, right? And you are given these data, and we want to test the effect of vacation. So whether it is a vacation or not. So we were going to test the effect of vacation. So whether on weekends the number of road accidents are higher compared to weekdays, or sorry, yes, on weekends whether the number of road accidents is higher compared to weekdays, right? So our hypothesis is that vacation affects road accidents. That if it is a weekends, then number of road accidents will be different compared to work days, right? So this is the model that we are using, the vacation effect model. It says that number of road accidents on ith day comes from a Poisson process with underlying rate parameter lambda, where lambda is equals to exponent of alpha plus beta into vacation I, where alpha comes from normal 2 to beta comes from normal 0, 0.5. Then we construct a null hypothesis model which looks the same, it's just that beta equals to 0. Okay, so these are our two models. We tested these models, we basically calculated Bayes factor using this Monte Carlo integration method here, and we got some interesting results. Now we are going to do the same thing using bridge sampling package. Okay, so let me show you how. So first fit your vacation effect model. I'm going to call it M1 full. Basically it's what I mean is it's a full model. Basically it's not leaving out any parameter. Okay, you can call it fully constrained. Basically there are conventions to call model with all parameters, whether with and compared to model with lesser number of parameters. So let's say M full, I will use BRM function. Okay, what is your dependent variable? So I'm just going to fit the BRM this model with BRM function first, right? What was your dependent variable? So let's say dependent variable is y, and y comes from vacation, okay, such that data is data frame y equals to y, vacation equals to vacation. Okay. Now family should be, what is the distribution we are using? Poisson. Family Poisson, and prior it's such that it's prior So what prior we would be using? For alpha, we had normal 2, 2. For beta, we had normal 0, 0.5. Oh, this would be 0.5. Why I had, okay, this is different. You change this. Okay. So alpha normal 2, 2. For beta, normal 0, 0.5, like that. Alpha is class intercept. Normal 0, 0.5. This is for class B. Yes, this is fine. So I've set up the priors. Now you can basically set up how many chains you want, number of cores. Okay, so all these hyperparameters of the algorithm. Okay. So this will fit this model I'm full. One more thing I want to do is this, that how many iterations you want in each chain. So actually I should increase the number of iterations, because as I told you that base factors are often unstable. So if you have more iterations, that would be better for estimating the base factor. We saw this in Monte Carlo integration as well. We had to take around 5 lakh samples, so much more than what we typically have for posterior estimation. So that's why I would recommend that increase number of iterations to at least 10,000 or even 20,000. Okay, at least not less than that. And warm up could be lesser, let's say 2,000, because it's a simple enough model. Okay, so this will give me M full. Now one more thing I need to do, I need to save all parameters. Save parse. True. So save all parse equals to true. You want to save all the parameters. So this is important for doing further, for calculating marginal likelihood and other things. Okay, so let us fit this model. Take a little bit of time, but not too much. I think it's already done. Let's see. Don't want to do it again. So this was the output. So what is the estimate for parameter beta? So the effect of vacation comes out to be positive between 0.10 to 1.02. This is good. And right, so the 95% credible interval is consistent with the prediction of our hypothesis. Okay? But let us check it using base factor. Let us compute evidence using base factor, because without base factor we cannot claim that there is evidence for this hypothesis. So we will fit the null model now. Okay, we will do the same thing. What will change? We will remove this prior on beta because now beta is assumed to be 0, and we will remove this thing from here, effect of vacation. Okay, just that y comes from let's say a Poisson distribution where lambda depends only on alpha, like that. So let's wait for it. Once you get M null, then you can compute base factor using bridge sampler. Yes, so this is done. If you want, you can take a look at the summary. We are interested in calculating base factor, right? So base factor can be calculated using now bridge sampler. So bridge sampler is a function in the bridge sampling package. So what it would require? It would require the fitted object M full and M null. So this is the output of the BRM function, right? So this is called BRMS fit object. Basically, this is a trained model in a way, right? It has all the information about posterior distributions. Okay, so M full, M null. So two models that you wanted to compare are being written here, but these are fitted models, BRMS fit objects, right? And then I use this function bridge sampler. So when I compute this, when I run this, what happened? M full is there, is M null there, M null is there. Let us try to do separately. This working? Okay. So this is ML1. So marginal likelihood for model 1. Let us compute marginal likelihood for model 2. Okay. So let's see what is the output of this ML1. Bridge sampling estimate of log marginal likelihood is 16.64. This is for model 1. And for model 2, bridge sampling estimate of log marginal likelihood is minus 18.82. Right? So this is log marginal likelihood. There should be a function to calculate their overall. Yes. log ml. This is log ml of model 1. This is log ml of model 2, right? If you want to calculate base factor, then it would be exponent of log marginal likelihood of model 1. Okay. So this would give you raw marginal likelihood of model 1, which is this, right? And divided by exponent of log ml of model 2. So this comes out to be 8.85, right? So approximately that's the value we got using Monte Carlo integration as well. So this is the base factor in favor of model 1 compared to model 2. Okay. So BF12 we got is 8.85. Okay. You can check it. So using Monte Carlo integration, what was the value that we were getting? So for the prior, beta normal 0, 0.5. Basically same model. So around 9, 9.22. If you run it again, you might get it slightly less than 9. Okay? So that doesn't matter. And the same number we were getting using bridge sampling, 8.85, around 9. Okay. All right. But the main point with the bridge sampler package is that it would work for even more complex models for hypothesis testing. Even you have hierarchical complex model, it would work for that, because all you are doing is that you are fitting the model using BRMS first, right? And then using this package, you are calculating marginal likelihood for each model. There is also a way to directly compute base factor given two models. I don't know why it is not working, but it's possible. But here what we have done, we have calculated marginal likelihood for each model using bridge sampler package, and what we pass on as input is the BRMS fit object, right, for each model, and that gives us marginal likelihood for each model. But the main point is that it can work for even more complex models. For example, consider this, that you have this word recognition data, okay, which looks like this. So this is data where participants are asked to read some strings on a screen, which could be a word or non-word, and their task is to recognize correctly whether it is a proper word or it's a non-word, right? And what we are recording is their recognition times. How much time do they take to recognize whether it is a word or not? Our hypothesis that we want to test is that whether high frequency words are recognized faster than low frequency words. That's the hypothesis, right? So how do we test this hypothesis? First, we separate out words from this data set and then construct this Bayesian model. Let us call it lexical access hypothesis model, right? So this model assumes that recognition time for the ith word comes from a log normal distribution with parameter mu I and sigma, such that mu I is equals to alpha plus beta into frequency of the ith word. Okay, so that's the let us call it the lexical access model. And the priors will be then prior on alpha is, because we're using log normal distribution, so let's say prior on alpha is 6, 1, and prior on beta is, let's say, 0, 1, okay, and prior on sigma is, let's say, 0, 0.5. Okay, so this is the lexical access model. Now, in order to test the hypothesis whether there is an effect of frequency, we need to construct a null hypothesis model or some other reference model. So null hypothesis model would be everything would be same, it's just that beta would be assumed to be equal to 0. Okay. So now how do we test this? So we first fit the lexical excess model. So let's say which is given by this, right? So family would be log normal here. On intercept, we had this prior normal 6.1. On beta, we had prior normal 0.1. Here we had prior normal 0.5. Right? Everything else is fine. Number of iterations would be increased. So let's say 10,000. Warm up are 2,000. Okay, rest is fine. So this would be AM1. So you can call it the lexical excess model. Okay. This is our full model. Let us fit this. Oh, sorry. Actually, I need to fit it on dat.word. So on a different data frame. Yes. And for null model, how would you construct the null model? So let's call it am null. Everything else would remain the same, but you can remove this beta. And here you can remove the effect of frequency. Right? So that would be your null model. And now to compute marginal likelihood for model 1, it would be bridge sampler M1. Marginal likelihood for model 2 would be bridge sampler M null. So we do exactly the same process as we did before. And this will test the hypothesis whether there is a significant effect of frequency or not. Okay. There is although one challenge here, which is that I did not do save all parameters equals to true, so which sometimes creates a problem. Because all these methods where they compute marginal likelihood or ELPD or cross validation, they require you to save all the parameters. So this one takes some time because there was a lot of data in this file data in this object date.word. We loaded this from word recognition data.csv, and it contained data from multiple words and multiple subjects. That takes a slight bit of time. You can wait for a couple more minutes. But this is something you can practice yourself. It's almost done, it seems. So 80% sampling is done for a couple of chains. Now 80% sampling is done for all 4 chains. %. Yeah, it's done now. All right. So let's see if it is working. Yes. So now it's trying to compute the marginal likelihood given this model M1. We also got some effect of frequency here. So the 95% credible interval is 0.39 to 0.43. Okay, so there is an effect of frequency as per 95%. So basically, this credible interval is consistent with the prediction that there would be an effect of frequency. That's all you can say. Okay, so now we have gotten marginal likelihood for model 1. Okay, so which comes out to be minus 71477.75. So if you do the exactly the same thing for the null model as well, you will get marginal likelihood for the null model. Okay, and then you can basically do the comparison. All right, so that concludes our lecture on Bayes factor. What I discussed was that how Bayes factor is one of the method for model comparison, and this is actually a very handy method for doing hypothesis testing. So you can test whether there is an effect for some factor by comparing a full model against a null hypothesis model, which assumes that the effect of that parameter, effect of that predictor is 0. Okay, these are called nested models. And you can compare these models using Bayes factor such that you compute the ratio of their marginal likelihoods under different prior assumptions on the parameter of interest. Okay, so if Bayes factors are, let's say, greater than 3, then you can claim that there is some evidence for this full model against this null hypothesis model. Okay, so this is a very useful tool. This can be even used to compute evidence for no effect of something, right? You can claim evidence that there is no effect of X on Y, right? And to do this Bayes factor analysis for more complex hierarchical models, we can use packages, already available packages like bridge sampler, right? So we'll fit our models using BRMS, and then we can compare those models using bridge sampler package. Okay. All right, so I will stop here. So here we have completed our lectures on model comparison. In the next lecture, we will start the last part of this course, which is hierarchical models. So we will discuss what are Bayesian hierarchical models and why they are useful. Actually, for hypothesis testing, we always use hierarchical models for at least in linguistics experiments. That's the practice that we have been following for last decade or so, and for very good reasons, because they are better likelihood assumptions compared to a model which does not assume the hierarchical structure. Okay. So we'll discuss about it in the next lecture. Okay, thank you very much. I'll stop here. Thank you.